to solve a system of ODEs, we need to do it in the following way. So you have y prime equals to a times y, where in this case, this a, it's known as the coefficient matrix, and y will be your y matrix. And as you can see on the screen, we have y1 prime and y2 prime, that's your first matrix, and that's equal to the a matrix times the y matrix. And you can see later on, the a matrix, you have the 4 coefficients, or the matrix is a 2x2 matrix. And basically, you'll see an example in a little bit, but those 4 letters, the a's, they're going to be replaced by whatever coefficients you have in your equations. So as you can see, we can use this method to break a second order ODE into 2 first orders ODEs, or we can also solve this one, use this one to solve 2 first orders ODEs simultaneously. Of course, you can increase the size of the matrix and you can solve higher orders, third orders, fourth orders, and so on. You can solve more than 2 first order ODEs. You can solve multiple first orders, second orders, etc. So this system is pretty powerful. At least on today's examples, we're going to be solving a second order ODE by breaking it into 2 first orders. But you can see that this example is something really practical that we can be using to solve multiple equations at the same time and get all the answers that we need. So to solve this one, the first thing that we need to do is identify whatever that matrix A is. So depending on the problem, we'll identify the matrix A, and then working from that, we're gonna be able to solve everything that we need. So another step, it will be to find our eigenvalues, which we can find by solving the determinant of matrix A minus the product of lambda times the identity matrix I. And if you remember, the identity matrix is nothing but a matrix of ones on the diagonals and zeros everywhere else. So once you multiply that times lambda, basically will be all the diagonals, coefficients minus lambdas. After we have our eigenvalues, or that will end up being our roots, we're gonna find our eigenvectors, and those vectors are gonna be basically what it's gonna be multiplied at, at the end to find a regular solution. And to find our eigenvectors, we'll instead do solving the equation of matrix A minus lambda times I, everything times X. And you'll see later on how we're gonna be doing this. So let's look at our first example. So we have here this second order ODE homogeneous equation. We have y double prime plus 8y prime plus 15y equals to 0. So we need to solve this one. We are going to be breaking this second order ODE into 2 first orders ODE. So my first step that I do is basically I write my variables that I will be using. In this case, I have y1 and y2. And basically y1 will be substituting any y that I have present, and y2 will be substituting any y primes that I have present. And usually when you have to break a second order ODE, this is like a step that always needs to be done. Then since we are working with we need basically 2 first orders ODEs, I will take the derivative of each one of those. So the derivative of y1 will be y1 prime, and basically that will equals to y prime, right? And y2, we derive the derivative of y prime will be y double prime. And basically we already know what each one of those is. So because y1 prime is equals to y prime, and we already have a definition for y prime, you can see that this will equal then to y2, correct? And then for y double prime, since we don't have a definition for that one, basically we need to get that one from the equation. So what I'll do is I will basically set everything on my original equation. I will send everything to the other side and just leave the y double prime by itself. And you can see that I will get now that y double prime is equals to negative 15y minus 8y prime. And then I can rewrite here that in my equation. And instead of writing them as y and y prime, you can see I will be substituting that y for y1 and then that y prime for y2. And once I will rewrite everything in clean as you see in red. And now this is my system of equations that I will be solving. As you can see, we have y1 prime is equals to 0 y1, because in my original equation, you can see that there's no If you see here, there's no, what's it called, y1's present, there's only a y2. So that's why we only have plus 1 y2. And then in my second equation, y2 prime, we have negative 15 y1 minus 8 y2. So that is my equation. That's my systems of equations. And that's what I will need to do and to put into the matrix. So you can see, basically we'll do the whole matrix, y prime matrix equals to a matrix times y. You can see that here my coefficient matrix A, it's just the coefficients of the numbers that I have in my equation. So you have 0, 1, negative 15, and negative 8. And this is basically what we do to put the system in matrix form. It will look something like this. And now this is the step where I will now continue solving the eigenvalues and the eigenvectors and then my general solution. All right, so to solve for the eigenvalues, you can see we need to take the determinant of lambda of matrix A minus lambda times I and set that equals to 0. So once again, we do the determinant, and you can see that doing this, only the diagonal numbers, the numbers in the diagonal, from upper left to lower right, will be the only ones that you will subtract the lambda, because that's basically the way the identity matrix looks like. So I have 0 minus lambda, 1, negative 15, and negative 8 minus lambda. And since when doing the determinant, you know that we need to do a cross. So 0 minus lambda times 8 minus lambda, negative 8 minus lambda, minus negative 15 times 1. You know, we do a cross. So basically how it looks like, right? The determinant, we're taking the product across. And once basically we multiply everything here in my equation, I will be getting this. And if I just rearrange, you can see my equation becomes now lambda squared plus 8 lambda plus 15 equals to 0. And you can see that whenever you're breaking a second order ODE, you know that you're doing things right, because this looks like the characteristic equation of that equation that you started with. And if that's the case, then it means you are doing a good job. And this basically only applies whenever you're breaking a second order. So just like we did in different problems, we're gonna find the roots of this equation. So we need now to factor it out. We're gonna get lambda plus 3 and lambda times plus 5 equals to 0. And then solving from the lambdas or the eigenvalues, we're gonna get negative 3 and negative 5. And this would be my eigenvalues. Now I will take each one of these eigenvalues, and for each one of my eigenvalues, I will find an eigenvector. So let's start with lambda 1 equals to negative 3. So you can see in order to solve for my eigenvector, I will do solve, and this will be the difference between matrix A minus lambda times I, everything times x, and then that equals to 0. All right, so you can see here I have an augmented matrix where I already include the zeros. And once again, only the numbers in the diagonal are the ones that will have the lambda. And in this case, it's not a determinant anymore. This is an actual matrix. We're doing matrix multiplication. And you can see that wherever the lambda is there, we're gonna basically substituting that for whatever value of the eigenvalue that we have, which in this case is negative 3. So we have 0 minus negative 3, 1, negative 15, negative 8 minus 3, 0, 0 times x1, x2. After we simplify, we're gonna get 3, 1, negative 15, and negative 5, 0, 0 times x1, x2. Okay, so you notice here that we have now our new matrix, our new matrix A. And what we want to do, it's basically we want to get rid of the second row. We want to eliminate it so that we only have one row that we can then work to find whatever x1 and x2 will be, which will be our set of eigenvectors. So to get rid of second row, you notice that if we multiply the first row times 5 and then add it to the second row, basically we're going to get rid of that one. So basically we're doing Gaussian elimination. And you can see now we have 3, 1, 0, 0, 0, 0 times x1, x2. And one other thing you notice here is that these two rows, the top row and the bottom row, they are basically the exact same pair numbers, but just times a a multiple of -5. You can see 3 times -5 is -15. 1 times -5, it's -5. So usually if you're doing things correctly, your two rows will be essentially the same, just that one of them will be a multiple of each other for both numbers. All right, so now from here, we're gonna multiply our matrices together. We're gonna end up with 3x1 plus 1x2 equals to 0. We basically solve for x2, or we set them into we solve things, move things around, and then we say that we assume that if x1 it's 1, right? We always assume like the simplest value we can get. If x1 is equals to 1, plug it in, and we're gonna get then that x2 is equal to -3. And thus, this is my first eigenvector, which will be 1 and -3. So now we're going to do this again, but for lambda 2 equals to -5. So now we have lambda 2 equals to -5. We're going to repeat the same process once again. You can see we have the same matrix A as before, same lambdas, everything, but now instead of that lambda being -3, we're going to substitute for -5. So we have 0 minus -5, 1, -15, -8, minus -5. After we simplify, we're going to get 5, 1, -15, -3. And let's just check. It seems that both rows are the same. The bottom row is just 3 times as much and negative as the top row, right? 5 times -3 is -15. 1 times -3 is -3. So we are doing things correct. They're the same row, essentially, just that one of them is a multiple of the other. So let's get rid of the second row. So to do that, we need to multiply the first row and add it to the second one. And that will give us the new matrix of 5, 1, 0, 0, 0, 0 times x1 and x2. So after we do, our matrix multiplication, we're going to end up with 5x1 plus x2 equals to 0. We solve for x2. And once again, we assume that if x1 would be 1, then x2, in this case, will be -5. And thus, my second eigenvector is 1 and -5. And of course, you can assume any other value for 1. You can assume one value for 2 and then so for 1. But if you just want to keep things consistent, we assume that x1 is 1 because of the simplest value. But of course, since these ones keep, they're the same vector, if you assume x1 to be any other value, x2 will be a proportional value to it as well. All right, so it's time to find our general solution. And the general solution has this form. So we have then that it's going to be a matrix solution. So y1 and y2, they're equal to C1 times our first set of eigenvectors times e to the first eigenvalue times x plus C2 times our second eigenvector times e to the second eigenvalue times x. So if we substitute everything that we found out together, you can see this is the value now. So we have y1, y2 is equal to C1 times 1 and -3 times e to the -3x plus C2 times 1 and -5 times e to the -5x. And this is basically my general solution. And you will notice that since here what we did is we broke a second order ODE into two first orders, the solutions that we will get, if you remember from the very beginning, y1 was equal to y, and y2 was equal to y prime. Therefore, the two solutions that we get are the general solution and the derivative of that general solution. So you can see here that y will be equal to C1 e to the -3x plus C2 e to the -5x, just the numbers on the top, the first set of the vectors. And then y2, which is equal to y prime, will be its derivative. And you can see that if we just multiply across, basically what you get, it's exactly that derivative. So once again, this is a problem in which we broke up a second order into two first orders. We're going to do a problem later on where we're just solving two independent first orders. but the process is exactly the same. So I hope that this video was helpful. Stick around to watch the second video later on. And as always, good luck.